as Eric said, I'm going to be giving an overview of the SPoT program and highlighting some of the initial data that we've collected. With me here are my co-authors and the people that work with me at UC Davis at the Marine Pollution Studies Laboratory. We're actually down on the small laboratory on the Big Sur Coast, satellite laboratory of UC Davis. And Karen Larsa and Shakura Azimi are program managers at the State Water Board. So some of these slides are going to duplicate what Eric just introduced, said in his introductory remarks. Let me get this straight here. Again, it's a statewide monitoring program, and it's part of the surface water monitoring, ambient monitoring program, focusing on sediment, contaminants, and toxicity. And I'll explain why we're focused on sediments as I proceed. What we're doing is determine long-term trends in stream contaminant concentrations throughout the state, and then relate various water quality indicators. It's basically sediment chemistry and toxicity to land use patterns. And so we've established a network of sites throughout the state to serve as a backbone. And what we're trying to do is collaborate with local, regional, and federal monitoring programs to get more bang for our buck. Okay, Eric said it's based on the NAWQA design. NAWQA is a USGS National Water Quality Assessment Program. And so I just emphasize that is using a directed sampling design rather than the kind of design you might see in EMAP and or the NOAA and Trends program. We're using integrator sites because we're trying to focus on understanding causes of water quality impairment, and we're trying to connect that with land use patterns. And we some example data sets of how we're doing that as we proceed. So to serve integrator sites, we've located these sampling stations at the base of larger watersheds throughout the state. And the idea is that we're going to be able to detect changes over time by going to the same station over a number of years. We use a network of sites that provide the statewide context for findings of local and regional programs. So we're trying to use the SPOT combined with local and regional data, same stormwater monitoring programs or other swamp regional monitoring programs, for example, to look at these results and then put that in the context of statewide trends. Having target sites allows some flexibility to match data with these sites. What I want to emphasize initially is we're trying to get more linkages, just so we have more bang for our buck. So within SWAMP, SPOT program is linked to the Perennial Streams Bioassessment Program, and the program run by Pete Odie. And it's also linked to a certain extent with the Bioaccumulation Program, which is called the Bioaccumulation Oversight Group, BOG. That's a tissue monitoring program. So we try to, at time, what we want to do with SPOT is use the SPOT data, take a look at bioassessment data, take a look at tissue concentrations over time, and see these three different disparate type data interrelate in areas of the state. And we're also combining that with regional monitoring programs. And then in terms of other non-swamp linked programs, we have some overlap in site selection with the Southern California Stormwater Monitoring Council, and with the Bay Area, the same thing, the various stormwater monitoring agencies. And then the other linkages include stations in the Central Valley in Region 5 and stations on the Central Coast in Region 3 that are agriculture monitoring stations related to the ag waiver programs. Or non-swamp linkages, and so those of you out there that might be doing monitoring that think there might be a way to link your stations with SPOT, we're all on that and would really like to encourage more communication on that. In terms of regulatory linkages, SPOT data provides relevant information for impaired water bodies listing for the 303D program. for statewide status and assessment programs, the 305B program, and provides information that regional boards can use and federal agencies can use for TMDL source identification and causes of impairment. So it is basically to pick the base of the watershed sites, integrator sites, and we have approximately 100 right now. It varies somewhat. 5 of the sites are also being sampled to look at temporal and spatial variability, so that's a subset of those 100 sites. And so we're covering about 50% of the major HUCs in California, and that's the USGS designation of hydrologic unit code, so they're basically the bigger watersheds. And what we're doing is sampling once per year for all of these sites, doing toxicity tests with this little ampod, Hyalella azteca. The Hyalella occurs naturally in the major watersheds we're sampling, so it gives us a good linkage to resident macroinvertebrate communities. And then we're doing sediment chemistry, which includes organochlorine pesticides, organophosphate pesticides, pyrethroids, metals, mercuries, and pHs at the urban stations. And for this information, and we're doing correlations between land use, contamination, and toxicity. And then as time goes on, as we develop multi-year data sets, we'll be able to look at trend analysis over time to see how land use patterns change and how that affects contamination and toxicity. So our sampling is pretty straightforward. We're out there in waders most of the time. A couple of the watersheds we're using a small boat, but for the most time we're walking in with waders and doing hand sampling. Here's Bryn Phillips sampling with a polycarbonate core. We used hand cores. This is the major method we're using, depending on water year and depending on what's going on at the particular site. This happens to be a fairly nice. Not all the sites look this good. I'm hoping everybody has seen the whole slide, because I'm not, and I think that's probably just because if I do this, yeah, well, I think everybody can see the whole slide. We're in our 4th year of sampling now. We're just completing this week final sites. So how can I improve this? Eric is saying he can't see it either. We're in full screen view. This is cut off. I apologize.
It's the text. It's not the slide.
Yeah. Well, I know what to do about it.
We just have to live with it.
Yep. Sorry about that, everybody.
If you can go back to, this is the way it was.
How do I do that?
Button at the
You fit to her?
Yeah, got it?
Yeah, to change anything. Okay, I see. Sorry about that. So, it's these green stations marked on this map are reference sites: the Smith River in Region 1, Lagunitas Creek in Region 2, the Tuolumne River, Chesapeake Creek in Region 4, and the San Jacinto River in Region 8. Comparisons between these reference sites and all of our other stations. A little bit of our results from 2008. At the very end of this talk, I'll show you the final, which is now available from the 2008 data set, or nearing its final stage of preparation. So what we found, these are color-coded: green, yellow, and red. And red is the worst one. 23% of the stations were toxic. We had a subset of stations. We didn't have full funding. 10% of the stations were toxic, and then 2010 back to approximately 100 stations, and 2% of those were toxic. And I said on the slide that these are samples that were tested at 23 degrees, and I'm going to get into the relevance of that as we proceed. A subset of samples tested at 2 temperatures. So at 2010, we did 25 stations tested at a lower temperature and compared these to the standard test protocol of 23 degrees C. Degree C is the temperature that USGS selected when they first developed the protocol for high-level Azteca. And we know with pyrethroids that they're more toxic at lower temperatures. So pyrethroids have been to be sort of a growing problem in California's watersheds. We're using this diagnostic tool to just indicate to us whether we're seeing more toxicity at the lower temperature. The mechanism is the animals metabolize slower at colder temperature, and they're not able to break down certain classes of pesticides like pyrethroid pesticides, and that's why they're more toxic at a colder temperature. The same is true with organic chlorines like DDT. The opposite is true for phosphate pesticides. So this is the same data in tabular form. You can see on the left here that the distance at 15 degrees C versus distance at the standard temperature. And you can see a lot more toxicity at the colder temperature. 2% stations were highly toxic at 15 degrees versus 4% conducted at the standard temperature, and 6% had some degree of toxicity compared to the control using a t-test. 67% of the stations were toxic, then twice as many as we saw with the standard test temperature. So the final chemistry from 2010. So we can't relate that to what contaminants are in those 2010 samples. This is related to pyrethroids. Every other comparison we've made in this regard has shown pyrethroids to be the culprit, but we'll have to wait for those data. Now, a similar presentation at DPR a couple months ago, and one of the participants in that asked me, what's the significance of this statewide? And so we queried the swamp database, 1,000 samples. These are samples that have been tested as part of, or sampled as part of routine swamp monitoring over about a 10-year period. So present discrete daytime temperatures. And you can see here the region on the left and the average temperatures in these regions from these swamp samples are on the right. The overall average temperature statewide was 15.9 degrees. And then a lot of the regions, the northern regions, tend to be a little cooler. Always. And so we're just trying to argue here that this idea of more toxicity at colder temperatures is relevant, and is probably because when we're out in these watersheds, they're interacting with these pesticides, with pyrethroids in colder temperatures. They're metabolizing slower, and so we think this probably plays a role in, or could be playing a role in situ toxicity in the state. And I'm going back now to data from the 2008 SPoT data set. This just shows you some pyrethroids. These are all of the pyrethroids that we've analyzed, summed together. And what I have here are toxic units color-coded. Unit in this case is where we take the individual LC50 for an individual pyrethroid and divide the concentration that we've measured in the sample, and that do an individual toxic unit. So if it's the LC50, it's equal to 1 toxic unit. If it's the LC50, it's a toxic unit. And with pyrethroids, their toxicity is additive. So when you have more than one pyrethroid together in a sample, their toxicity is additive. we find when you're above about 0.4 toxic units, you start to see toxicity in samples. And so we've sort of colored them here in this state map. It's a little difficult to read on this small screen. But what we found was about 50% of the 2008 samples had some measurable pyrethroids in them. I slide just to give you some perspective on pyrethroid toxicity. I'm going to be sort of beating the pyrethroid drum here for a little bit of this talk because it's playing a pretty large role, at least in our 2008 and we think our 2010 data set, in terms of explaining toxicity in our SPoT samples. So they're toxic down to the low parts per trillion range, 1 or 2 parts per trillion pyrethroids in water. Pyrethroids like bifenthrin, for example, are toxic to our animal. It's about a drop of water in an Olympic-sized swimming pool, and a trillion is about 1,000th of that. So it doesn't take molecules of this stuff, of pyrethroids, to be toxic in water or in sediments. I'm just trying to include that here so you get some perspective on the implications of this statewide. This is going to be my pyrethroid slide, I think, but this idea of pyrethroid toxicity is because our argument is that we're likely underrepresenting the impacts of pyrethroids by testing at 23 degrees. We do that because that's the standard protocol temperature. But we see greater toxicity when we're testing at at something that's close to an ambient temperature, 15 degrees. And the other this protocol that we're using, the 10-day amphipod test, is it's an acute exposure. We're exposing them for 10 days and looking at growth and survival. We know from sets produced by the group that developed this protocol, the USGS group in Missouri, that the term chronic exposures are much more sensitive. We have comparative data for pyrethroids, but we know that in terms of contaminants in general, the 28-day exposure is a lot more sensitive. And that's because actually that's in the steady weighting protocols, at least for brackish water applications, and they're moving towards using the 28-day protocol for more brackish habitats. And that information just emphasizes the fact that anybody that's out there involved in monitoring, if you're interested in pyrethroids, you really need to make sure you're with a lab that has low detection limits. You need to be around 1 or 2 parts at least, otherwise you're going to be underestimating what's going on in your watersheds. That wasn't my last pyrethroid slide. We also know that, as I mentioned earlier, our SPoT sites a lot of the sites are located at the base of watersheds, and a lot of those, because they're in the coastal regions, are near the coastal environment. So I've just here some examples of some sites that we have data from in the marine environment that are adjacent to our SPoT sites where we're seeing toxicity associated with pyrethroids, and they include San Diego Harbor, it's Whistler Creek, and Upper Newport Bay downstream of San Diego Creek, Iona Creek Estuary, which is monitored by SQUIRP, and then the Sea River Estuary. All of this evidence, and the citation there is a report that we just published for SWAMP on toxicity in California waters, and that's available soon through the State Water Board. Then I spent a little bit of time just talking about the ecological relevance of the toxicity tests we're doing. It's a laboratory exposure. So people often ask, well, what does it mean? What is it telling us in terms of what's going on in the environment? The animal we're using, the amphipod, Hyla elasteca, does occur in our watersheds. So there is a direct linkage in that regard. But then just listed here some studies, most of these California studies, but the top one is a study done by Chris Ingersoll's group. They're the ones that developed this toxicity test protocol. And from here, triad data set just means data sets where we have chemistry, toxicity, and benthic community characterization, so characterizations of macroinvertebrate communities. Ingersoll's group did some spiking experiments where they spiked mud with different goals, stuck them out in microcosms, and then looked at colonization rates and related that to sediment toxicity. And they found there was a direct linkage there between lack of colonization and increased toxicity with this toxicity test. Then we've done triad sets in the Salinas River a couple different times, the Santa Maria River, the Santa Maria Estuary. All these have shown linkages between laboratory toxicity and impacts on benthic community structure. In cases, we've done toxicity identification evaluations and shown that it's related to specific pesticides. The vast majority of those are organic pesticides like diazinon and chlorpyrifos and pyrethroid pesticides, a whole suite of pyrethroid pesticides. Done similar studies in covering creeks in the Central Valley, found similar between the laboratory results and field impacts on Hyalella in his samples. But I also emphasize Paul has done a couple of different studies at some of the same sites Don Weston's worked at, and his conclusions differed. He found that benthic communities using studies were much more heavily correlated with HAT than with contaminants. There's sort of these are examples. If you're interested in these citations, you can email me and I'll provide you with these papers or linkages to them. Okay, switching from toxicity now, a part of what we're trying to do in the SPoT program is relate what's on at our integrator sites to land use upstream. And so the land use data we're using are the National Land Cover Database and the Impervious Surface Database. These drainage delineations and land use characterizations, all this information is put together by Pete Odie's group at Cal State Chico. So what I have here is the little red dot as an example, and one of our watersheds is the integrator site. And then the different radii here are different area delineations. So the first circle, half circle there is the 1 kilometer delineation. The next one, 5 kilometer, and then we have a whole watershed delineation. And the idea is that we can do correlations between land cover and different measures, chemical contamination, sediment contamination, or sediment toxicity, based correlations with these different land uses at different distances from our integrator sites. Are the different components of our reference sites on top. And so the red PI are the urban areas. The next color is, I guess that's orange, is it's open, and then we have pasture land, row crop land, and then other, and the other just doesn't fit the other categories. We see, we have the same depictions here for our reference sites from 1 kilometer out to 5 kilometers out to the whole watershed. And you can see in the reference sites in the whole watershed, most of them are other, and it's basically not developed land. And there are characterizations, and those are basically just not the reference sites. Your mixes depending on how far out you get from our airplane sites at the base of watersheds. So there's pictures here to give you some of the difference in our station. So this is Bayona Creek down in Los Angeles. I'm trying to grab this little pointer here. I don't know if that's working. That's not too far upstream from the Pacific Ocean. And we have is Walker River or Pajaro River at the Walker Road, which is in our area up here in Region 3. And this is highly, it's heavily with row crop agriculture, also quite proximate to the Pacific Ocean. And then, of course, we have mixture sites throughout the state, and for those sites are reference sites. Data from the 2008 report that John Hunt wrote, and what I have here are just correlation values. And what we're trying to show here is, if we're looking at are on the left-hand side here, things like pyrethroid pesticides, survival of our amphipods, PCs, or total T organic pesticides, and then we're how these different measures are correlated with our different variables. And the variables are either on the watershed scale, which is WS, or on the different distances from our site, 1 kilometer and 5 kilometers. And take-home measure from this, or information from this, is that the correlations between things like pyrethroids, amphipod survival, PCBs, or DDT, is that we're more strong correlations between land use than we are between the other land use categories. To us, the high of this is that on a statewide level, contaminants and toxicity correlate with urban areas. Now, concluding this slide too, and this is from this recent 2011 statewide toxicity. It basically evaluated all of the swamp data and also included this SPoT 2008 data. And this is a box and whiskers graph, and you can see the dotted line here are mean values. And so, what we're looking on the axis is, or on the y-axis is the most toxic sediment samples. It's a little bit of marine toxicity test data, but it's, I would say, our freshwater data with high-low azteca. So we see there's, if you look at the sites, the non-ag or urban sites, these are greater than 90% of the sites are not toxic. But if you the second agriculture versus urban, there's no significant difference between the two, which is different than what we found with just looking at the 2008 SPoT data. And so the idea here is that this is a larger data set than that SPoT 2008 data, and so to have great cover of the state. In this, not seeing a big difference between urban and ag, but in we definitely are with that 2008 data set, seeing much more stronger correlations with urban land use. We'll have to see on as we data through SPoT, we'll see if those correlations stick over time. A couple more examples here. Again, what we're trying to measure here is not only that are totally related to toxicity. I say in the most is PCB aren't a major concern for at least acute toxicity, but they're definitely concerned for bioaccumulation, and something that's detected by the BOG program. So including it in our long-term trends, because we want to see if there are changes over time with things that are problematic for bioaccumulation. And so there's an example data set just from 2008 showing distribution of total PCBs. And what we're is we're using guiding values that were published by Don McDonald in 2000, and they're called the threshold effects level, and the PL is the probable effects level. And these values, these guideline values, were developed by McDonald et al. Based on very large national data sets looking at the correlation between PCBs and freshwater sediments and likely effects on different components of ecosystems. Same sort of total DVTs statewide. So the idea able to look at these trends in these particular constituents over time as we develop a longer temporal data set. Nobody did this, but I included it because I just want to highlight the fact that we're using a growing data set that we're developing both our laboratory and then we're gathering data from other laboratories that specifically relates sediment contaminants to effects on ILL azteca. So we have LC50s for a whole suite of pyrethroids, a bunch of organochlorines, a couple of organophosphates, and at the bottom there is fipronil, and we have some values for PAHs. And the idea is we're not only using the sediment quality guideline values, but we're using specific LC50s so that we can something specific about a sediment sample and its the likely cause of toxicity in that particular sample. And we're continuing to build on this data set. This data, I just want to mention, if anybody's doing toxicity tests out there and interested in toxicity, we're more than happy to provide. These are just Excel spreadsheets we provide to you if anybody's interested in, with all the citations that back all these data. And for sediment toxicity, 2008 through 2010, 23 to 35% of the stations wide were toxic, 23 degrees. Remember from the 2010 table I showed you, we get much greater toxicity when we test at 15 degrees. 8 data, the measurement of toxic units, we definitely see pyrethroids as a cause of sediment toxicity, the high ILL azteca at many of the sites. And then on a statewide level, the urban land uses are the most highly land uses that are correlated with pollutant concentrations and toxicity. And this is just with that from that 2008 data set. So this slide here is the citation of the 2008 SPoT report. We're very final stages of review, so my guess is within a month this report will be available for anybody to download from the SWAMP's website. Include my contact information here. I guess this will be available when Eric posts this on the web, but it's pretty simple. It's anderson@ucdavis.edu. If anybody needs to contact me for any of this information. So I'll conclude with.
Thanks, Brian.
Sure. Sorry about those slides.
So for questions, you send those via chat, or you can send just unmute your phone and ask. Minutes for that. Brian, if you can type in your contact information into the chat, we can send that to participants.
Okay. Speakers, so I can type.
And unmute phone, it's *6. And you can send questions back to Brian or to everybody or myself. Have a already posted, hopefully by the end of the day, day or two.
Hey, Brian, this is Chris Stransky. Can you hear me?
Yeah.
And I was just curious, of the sites that show toxicity, have you done you have concurrent bioassessment data to see what ILL exists at those locations. We found some sites where it's toxic that are there, and we took those species, the animals that live there, and found out they were kind of resistant to pyrethroids. That'd be a good thing, but I was just curious on what kind of trends you may have seen.
Well, we haven't had a chance to do that at the SPoT sites, other than, like I mentioned, some of those SPoT sites are actually sites that we've studied in the past, in particular the ones in the Central Coast. On those, we've definitely seen a loss of total abundance, and then loss of certain key indicators. In the Saline Valley, we see toxicity to high level. We see a loss, for example, of not only high but certain mayfly species like Prochlorion, sort of thing in the estuaries that we've looked at. But that's one component that we're really hoping to get more data on as we progress and as the Perennial Streams Program gather data, at least that are close to our SPoT sites. We really want to get into those and take a look at the specific, maps and see what's going on with those. But got into that, statewide, definitely not. Yeah. I'm a little surprised to hear now saying that you're getting increases of amphipods. Are you just saying species that are examples where you're seeing?
I'm sorry, was it too? Yeah, we took Hyalella from the field where we were doing bioassessment sampling and concurrent toxicity testing. In toxicity tests, we've identified pyrethroids causing toxicity at site using cultured Hyalella. When we're out there doing bioassessment, lo and behold, there's Hyalella running around. So we collected a bunch of them and did some toxicity tests side by side with a couple pyrethroids and looked at the cultured species versus the ones found in the field. And the ones found in the field were a magnitude less sensitive to the pyrethroids than the cultured Hyalella.
That's really interesting.
It was interesting. I mean, that may not be a good thing, but I just haven't seen other data sets to look at correspondence between the species. And I think the presentation was really great, by the way. That was real informative.
Thank you.
Yeah.
You guys should write that up and publish it.
I've worked with, we need to do that.
I know you don't get paid to do that, but that would be really useful information for people out there, especially people like Ingersoll's group would be really interested in seeing something like that.
Right. Yeah, we've given a few presentations, but yeah, it's cool. It's kind of neat.
Yeah.
A question that was sent in via chat.
Okay.
What are the sites where you found Hyalella azteca?
So, in particular, where we found Hyalella azteca, I can't say we're doing that for SPoT. We're not actually doing bioassessments ourselves, so that's not a component of SPoT. But gave keen toxicity, the ecological effects. This is where we're also doing monitoring downstream of some of the sites. Obviously, some of those places are highly toxic places, so we're not finding azteca at them. But if we move upstream of where the key inputs are, we find them. I hope that. But in terms of the SPoT sites, for example, we might expect to see at some of those SPoT reference sites. We have bioassessment data from those sites yet. We're hoping goes on. Some of these stations are stormwater monitoring stations, and I think that's exactly what Chris Stransky was just talking about. I hope that as time we're going to be able to look at that bioassessment data, and it's going to be really interesting if we see correlated toxicity, or if, as suggests, there might be some increased tolerance with native populations of Hyalella.
Thank